All right, hello everyone. Welcome to Lecture 8 on Relational Databases. Last time we talked about load balancers, and to summarize that lecture, I said that we had completed by that point about 2/3 of the end-to-end view of a basic scalable architecture, which is to say we were talking about the front end, where you have a bunch of users coming in that want to connect to your service, and a load balancer hands those users off to many replicas of the service. There are different kinds of load balancers, global load balancers and local load balancers. When you have users that are literally being sent to one machine first before they're directed to a clone of the service, that's what we call a local load balancer, and those can be implemented either as reverse proxies or as NAT devices. Those are quite important, but they have a limit to the amount of scalability they achieve, so those are kind of mid-level scaling solutions. Those also provide some benefits for continuous operation, like reliability, and to allow the service to always have some working copy that it can send requests to. When we need scale beyond that level, like beyond just, like, let's say 100 machines, you need to move to a global load balancing solution where you have users using some kind of directory service that's distributed to find their way to a replica of your service. That the directory service could be either DNS, the domain name service, or it could be done through the IP address resolution, which is essentially the IP anycast approach, where we have the users are all connecting to one IP address, but somehow that IP address actually refers to multiple locations around the world. So that we were talking, load balancers is really all about scaling the front end, the connection point between the user and your service, getting a user to one of the many clones of your service. Earlier in the class, of course, we talked about how to make services scalable by making them stateless. If you make a service stateless, then you can implement it on thousands of clones, and the user can have its request go to any one of those clones equally because of the statelessness of the application. But when we made an application stateless, the way we did that was by pushing state down to a database. And we haven't talked about databases yet, or some kind of data storage. And that was like pushing the problem under the rug, or kicking the can down the road, depending on what analogy you prefer. Like, we kind of avoided solving that problem of sharing data and coordination, and said we would solve it later when we talked about databases. So now, this next big chunk of the class is about databases, to figure out how we can scalably handle state in a way that works for that allows all these, like, let's say thousands of clones of your service to access, to share data. Okay. So in this one lecture, we're going to kind of summarize some of the important parts of a couple of different database classes that are taught. The traditional computer science majors database class 339, as well as the CS-310 class that is taken by industrial engineering majors and other non-majors. So today we're going to be talking about defining relational databases, talking about the SQL language, and also about data modeling with relational databases. In other words, how to define tables to reflect your data. And that's actually something that is covered more in 217 than in 339. So if you've taken CS-339, you might have learned quite a lot about the internals of how databases are implemented, query planning, and indexes, and all that stuff. Whereas you might not have spent too much time thinking about how to use databases as a user. And this lecture, we're going to talk a little bit more about that. So, yeah, our viewpoint now is to learn a little bit about what happens inside the database, inside the implementation of a database, but only so much as we need to know to be a user of a database. In other words, that we're assuming that we're not writing the database ourselves, but choosing from an already existing off-the-shelf database, whether it's open source or commercial. Okay, because in practice, that's typically what you would do, unless you're working at a huge tech company that is kind of like innovating in that space, or you're working at a database company, right? All right, so let's go back to the architecture we've been spending a lot of time looking at, this Wikipedia architecture. And in this design, we had these green database servers on the back end that the main application was interacting with. And what was being stored here mainly was the text of the articles. By pushing the text of the articles back here into these shared databases, that allowed all these clones of the service to be able to accept edits and also reads in a simple way, because, if there was an edit that happened, what happened was we just modified the data in this database. And if there's a read, to get the contents of an article, we just fetch the latest copy of the article from the database and then render it in the application. So what we're doing with this database is providing coordination. In other words, we make an edit in one copy of the service, yet we are able to see it across all the different clones that are running, because that edit that happens in one instance gets copied to a shared location in the database, and all the other instances, when they read information about that article, they're going to read it from that shared place. Okay, so that's how coordination happens through a database. And this also provides persistent storage, because like normally we write our applications to interact with variables in memory. That stuff gets cleared when you reboot the machine. And also, if an application is stateless, by definition, it is not remembering, it's not storing state after the application is done handling a request. Okay, except it's doing so in the database. So the database is the stateful part of the system, and has the persistent storage. All right. So what the databases are handling, like I said, are both persistent storage and coordination, and these will turn out to be the biggest scalability challenges in our system, because load balancing is relatively straightforward. Running clones of a stateless application in parallel and putting them behind a load balancer, that is all that's pretty straightforward. We've showed that so far. However, scaling a database, we'll find, is a lot more challenging, and it will require you to make difficult choices about what kinds of databases to use, how to store data in those databases, how to coordinate things. The bulk of the difficult choices that you have to make in architecting a large-scale system really revolve around how you're storing the data and how you're updating the data that's persisted. Okay. All right, so to introduce that topic, we can review a little bit about the basics of computer engineering, which is to say how computers are built, and especially how data is stored in computers. And the important thing to know here is that computers have a hierarchy of storage, which is to say they have different kinds of storage. I'm showing them in layers here, so 5 different categories, where you have the uppermost type of memory, CPU registers, are the smallest, but also the fastest. And as you go down, you have different types of memory or storage, data storage, that becomes progressively bigger, but also slower to access. Like the delay between making a request and fetching data and actually getting the data back becomes longer and longer. And the reason for that essentially is spatial. If we think about this at a high level, so the computation in your computer happens inside of a CPU. So all your computation is happening here inside your CPU. On the right hand side, we see a die image, which is to say, like if you kind of take this case off the top of the computer and kind of slice apart the packaging, these are this is like the transistor level view, but zoomed out, because there are like hundreds of millions or billions of transistors in the processor. And in the processor, this one has 8 different processing cores, 8 different CPUs essentially. Within each CPU core, there is circuitry that executes your code. So it handles things like mathematical operations and conditional checks, like for if conditions, and branching, which is associated with ifs. To do all your like loops and calculations and like string manipulations and all that stuff. So your code is executed in here with this circuitry. And inside each core, very close to where the circuitry is to do the operations, there are registers that store data. Now, there's only a small amount of space there. The location that's closest to where the operations happen, the absolute closest locations are called registers, and those are limited in size because there's only a little bit of room close by. But the speed to access them is very low because electrically speaking and physically speaking, there's a very small distance to travel between where the computation is happening and where that storage is. So that in the CPU registers is where you can access stuff really quickly, and your compilers handle management of what data is stored in registers versus what is stored in RAM. So RAM is memory, and it's typically on like cards like this that are plugged into a motherboard, or it could be soldered onto a motherboard that is like all in one piece. Like if it's a laptop computer, typically these days, it's like one big circuit board that has a CPU soldered on there, as well as these like black rectangular DRAM chips. And so this is quite a bit further away. So it's like off chip across a big circuit board, and then so it's a few inches away, as opposed to being potentially just tiny fractions of a millimeter nearby, or like 1 millimeter away, very close by. There's some in-between types of memory called CPU caches. So this picture shows a shared level 3 cache, as well as on each core there's a level 2 and a level 1 cache. And that would be maybe on the side of this core. So it's like still pretty close to where calculation is happening, but it's a little further away where there's more space available. It's kind of like the suburbs of the CPU within commuting distance. But again, space there is limited, so you can only store so much there. After that, it has to go to this L3 cache. After that, you have much more space available off chip. This is the CPU chip. Off the CPU chip, you can add more chips these to store more data there. But as you get further and further away, it's slower. Okay. Now the CPU caches, the L3 cache, L2 cache, L1 cache, those are actually managed by the CPU itself. The CPU stores the most recently used data that is in memory, in RAM. It caches it in these caches, just like we talked about caches for CDNs and HTTP proxies and stuff like that. The same concept comes back here. The programmer doesn't have to manage those. It's actually, and the compiler doesn't have to worry about those. These caches are automatically used to store the most recently accessed data that's in DRAM. But this RAM also is limited in size, and it also is volatile. Volatile in the sense that when you turn your computer off, it gets erased. So it needs to have electric charge flowing through it, or to keep its data. So if you want data to stay on your machine when you reboot it, it needs to be stored to a file somewhere, and those files are stored on disk. It could be either a solid state disk or a rotating magnetic disk, and those are accessed in the same way, but solid state disks don't have as great a capacity. However, they tend to be faster because you don't have to have the spinning action of the disk to reach where your data is stored. Okay, so to summarize this, there actually are 3 different classes of memory that are managed in 3, or really 4, that are managed in 3 different ways. So CPU registers are handled by compilers, or if you write assembly code yourself, you would be dealing with CPU registers. Memory, RAM, is referred to by numeric locations in your code. So also, the compilers manage that. Storage on solid-state disks and magnetic disks is handled in a different way. Your programs don't access that directly. You don't have variables that refer to data on disk. Rather, you have special system calls, which are like functions that open files and read data off of files. Okay, and when you move from these smallest and fastest storage locations to the biggest and slowest, you have dramatic differences in the speed and capacity. So a magnetic disk is about 10 billion times larger than the CPU registers. It's also has 10 million times larger delay or latency. So in the same time it would take to read a register 10 million times, that's the time it takes to read just one thing off of a disk. Okay, so we want to avoid doing things, we want to avoid operating with these lower levels of the storage hierarchy. Sometimes you have to use them, of course, because you need the greater capacity that they provide. But in general, your compilers should be optimized to use these registers and small amounts of memory as much as possible. The less memory you use, the more of it can fit inside the CPU caches, which makes your program faster because you're working more with the memory that's on chip as opposed to going off chip. And similarly, you would prefer to use flash storage as opposed to magnetic storage because it's faster, although the capacity is less. Okay, so we still have big data that we need to store, so we do need these lower layers, but we want to use them as infrequently as possible. So if we have a lot of different kinds of data, the data we're going to use a lot, we want to store as close to the top of this hierarchy as possible, and the data that we're rarely using, we would end up putting in the lower levels of the hierarchy. And also the things that need to hang around after when we turn off the machine need to be in one of these persistent storage media. Okay. Right. So I got a little GIF animation here to show you how magnetic hard disks work. Now, these things used to be in every PC, in every computer, whether it was a laptop or desktop. Nowadays, your laptop probably does not have a rotating magnetic disk because solid-state drives have become cheaper, more widespread, and the capacity is actually pretty good. So you get much better performance from a solid-state drive, so that's why your laptop has one. You also get better energy performance, like you use less battery with a solid-state drive. But these rotating magnetic disks are not obsolete by any means. These are still what's used for all the big data sets that are stored in the cloud. So like your YouTube videos, Flickr photos, Facebook posts, all those huge data sets that are managed by cloud providers. Your Dropbox data, all that stuff is on spinning magnetic disks because it's just so much cheaper. There's so much more capacity on these per dollar than solid state disks. Although that may change over the years, but for now it seems to still be the case. But what makes these relatively slow is that the data, just like a music, an LP record, any particular piece of data is stored in one location on this platter, and in order to read it, you have to move this read arm to the right angle so it's on the right track, like the right circle. And also the disk has to spin around to the location where the read head is. So the tip of this arm is the only location where reads and writes are happening. Of course, there actually are a lot of platters that are on top of each other. It's kind of like a stack of pancakes. And there are a lot of these read arms that are together on this actuator. And so they can read in parallel off of the multiple platters. But again, you're only reading from the very tip of this arm at any given time, and you have to wait for the rotation. If you want to read from a different location, you have to wait for the disk to rotate to that location and also move the arm. Okay. So there's only a tiny bit that you're reading from at once. You can't read from the whole disk at once. If you wanted to read from the whole disk, you would move the arm to the edge of the platter, start spinning it, read all the tracks, and gradually move the arm inward. And for a disk like this, it would take about a full day or maybe 2 days to read all the data off of it. Okay. With the solid state based storage, whether you're talking about a solid state disk or RAM, you don't have anything mechanical, nothing moving, but there still are limitations to how quickly you can read this data. So like in RAM, if you want to read data, the connection to this data is through this edge connector. So see these electrical connections? There are like maybe a few hundred of them on the edge. These gold contacts. So at any given time, there's like 1 bit, let's say, that is presented on each one of these pads or contacts. So you have to cycle, if you want to read all the data that's in memory, even though the capacity of this stick might be like, let's say this one is 4 gigabytes, but a more modern one might be like 16 gigabytes or 24 gigabytes even, that's stored total on this card, you can only read a few hundred bits at a time. So you have to cycle through them as quickly as possible. There's a limit to the speed you can do that. So like there's a lot of data stored in both of these things, but the I/O is slow. The window you have into that data, the bottleneck through which that data flows is relatively small. So it's kind of like a huge warehouse with a tiny door. Okay, the little door in the case of the magnetic disk is the read head on this arm, and in the case of RAM and solid state disks, there's a little bit less of a bottleneck, but there still is a tiny door in the sense that this edge connector is smaller than is much smaller than the amount of storage cells there are on this whole thing. There are billions of different storage locations on these chips, and yet there are only a few hundred different communication lanes through which to communicate that data. Okay. Or if you're looking at a solid serial ATA connector, so that cable has I think maybe 4 wires on it, or some small number of electrical connectors to transfer data. So to get over some of the limitations of disks, one strategy you'll probably see if you work in operations, in storage, or in DevOps, if you set up your own data center hardware, you would see RAID. RAID stands for Redundant Array of Independent Disks. And the purpose of RAID is to overcome several shortcomings of disks. So disks have limited capacity. So these days, a disk might have a capacity at most of about 12 terabytes, which is big. But, of course, if you're a huge company with lots of data, you need more than just can fit on that one disk. There's limited throughput. Like I said, the small door or window into that big warehouse of data minimizes the amount of data you can transfer per second. So a magnetic disk can transfer about 150 megabytes per second, which if you do the math, like I said, is like a couple of days to go through the whole data set, which is, you might want to go faster than that, right? And there also is a high likelihood of failure with disks, especially for these magnetic rotating disks with the physical rotation. The average failure rate per year is roughly 10%. So usually, like within a period of 5 or 6 years, you would expect your disk maybe to have failed with a good probability, with like roughly 50% probability or 40%, something like that. But what RAID does is uses multiple disks kind of in parallel to solve these problems. There are different kinds of RAID, which I think would be covered in, when I teach operating systems, is covered in that class. And you can learn more about those online, but I'm going to just briefly give an overview. The idea here is to increase the capacity by making multiple disks available to store data. So instead of storing data on just one disk, you kind of split up your data and store it on a set of disks. That's kind of an obvious idea, right? But this is a way to do it in a very easy, elegant manner. You also can increase the throughput of access. Like if you want to read data more quickly, again, if you do that access in parallel, if you have already split your data across multiple disks, when you're reading, you would read it at the same time from all those disks. So that would make it, if you have 10 disks instead of one, you can read data 10 times as fast, right? Of course, if you only want to read 1 byte, that doesn't make it any faster. You still have to wait for this, whatever the latency is for reading 1 byte. So it doesn't increase latency, only throughput. You also can reduce the impact of disk failures by having multiple disks. Now, actually, if all you do is split your data onto 10 disks instead of 1, then you have made your likelihood of failure even greater, because if any one of those 10 disks fails, then you lose data instead of just having one disk that might fail. But if you're clever about it and introduce some redundancy, like parity bits, then you can tolerate the failure of 1 or 2 disks and still have all your data intact. Okay. And this works really well because a disk interface is very simple. A disk presents itself to the operating system as an array of sectors. A sector is a chunk of 512 bytes that you can read from. So it's basically just a big array of bytes. And you can easily take multiple disks and create that same abstraction of a block device, like an array of blocks. You can create a logical or virtual disk that the operating system has access to, and it can kind of treat it in the same way as a regular disk. If you have some kind of translation layer, that it's easy to translate from an array of one big virtual disk into distributing that to many smaller arrays of individual disks, which is to say. So yeah, just to make a cartoon out of it, I'm using the same kind of strongman picture as I did for load balancers, but it's the same kind of idea as a load balancer. So I like making it a parallel analogy. With RAID, we create the illusion of one really strong, big, fast, superior disk. It's a virtual disk. It's not really one disk, but the operating system has the same interface to it. Just like with a load balancer, we had the same interface of just sending HTTP requests and getting HTTP responses. With this storage array, we have the same interface as a single disk, which is to say it's a byte array, or it's a block device. So we send requests to read or write sectors within that big array of storage. But in reality, what we have is a RAID controller. Instead of the request going directly to a disk, it goes to a controller that's kind of like a load balancer. Depending on what the address is that you're reading or writing, the RAID controller will distribute it to one of the disks in the array. And again, a couple of these, 1 or 2 of these might be redundant disks that have parity information. Again, the details of that are beyond the scope of this class, so you might need to read or write from more than one disk at once. But in general, you could imagine that this request is reading from 6 sectors. You could split it up into a bunch of 1 sector reads from these 6 disks. Do those all in parallel, so there's less data for each one of them to read, So the work gets done in 1/6 of the time, right? And also you have the capacity that's 6 times greater. Okay. Again, normally you'd have some kind of redundancy, so it wouldn't quite be 6 because a few of these would be dedicated to for redundancy. But nevertheless, you'd have both. You'd have greater throughput and capacity than a single disk. Okay, and that could be done in a way that's like transparent to the user, which is to say that the request still looks the same as if it was going to one disk. Right, that's RAID. And you see this in practice quite a lot. So this picture shows a big database server that I maintained for Northwestern a few years ago. So this was 5 years ago. So it's not totally up to date. Like this is, you still could have a system like this these days, but you would probably, the individual disks would be larger capacity than they were 5 years ago when I was working on this. But anyway, so like what we have in this picture is at the where my hand, this person's hand is pointing. This machine here is a server. The one that has the gray, these are redundant power supplies here. I think those are power supplies. Actually, those might be disk-based. Anyway, there's a server here and there's a server here. So there are 2 computers here, actually. And one of them, this one on top, has within its case a bunch of slots for disks to plug in, like maybe 12 disks. But in addition, there are all these other chassis that have lots of other disks, and there actually are disks both in the front and on the back of these cases that are holding additional disks. So this one computer is actually plugged into about 300 disks through these external boxes of disks. And the way that happens is with this external SAS cabling. So the back of this computer has a lot of these cables. These cables plug into these other chassis that are holding lots of disks. There are different sizes of disks you might notice. Like in the middle here, we have these 3.5-inch size, not 3.5, 2.5-inch disks, which are actually rotated at a faster speed. On the top, we have the 3.25-inch disks, which are bigger and have more capacity, but they're slower. So these ones were actually used in a backup in this case, whereas these ones were used for high performance. But anyway, this is like one big closet-sized thing. You can see compared to the person's arm how big it is. And this is kind of like one big machine with lots of disks, although there's a second machine here that has a smaller number of disks connected to it as well. And all these disks can be used together by this operating system in a very simple way by creating a RAID array. Now, in reality, you wouldn't want 300 disks in one RAID array, so these are actually several RAID arrays that present themselves as different virtual disks. But there are only about 10 different virtual disks that were presented to this operating system from the roughly 300 different physical disks. So here's a schematic view of that. We have like this outer box represents the computer. The computer actually spans multiple boxes, like I said, because there are these cables that connect the additional storage units to the main computer, but it's still like logically one computer. That computer has multiple CPUs, so it's using symmetric multiprocessing, has lots of memory. It's running like one instance of database software or Relational Database management system. In this case, it was Microsoft SQL Server. But it's connected to lots of outside disks. This just shows some of them. Between that machine and all those disks, there is the ability to transfer data, but it's kind of a limited ability because these CPUs have limited I/O bandwidth. So I/O means input-output. So theoretically, the maximum you get is limited by the number of PCI Express pins on the chip. It's about roughly 80 gigabytes per second is what you can transfer between storage and CPUs, which is actually quite a lot. But for some applications, that might not be enough. So the way these storage systems work, you can actually connect as many disks as you want to the computer. There's really no practical limit. But what is limited is the I/O bandwidth of the CPUs. So this 80 gigabytes per second is never going to get any better for this particular generation of CPUs, which is a couple years old, but I think these days it's still basically the same. So although you can add more storage as much as you want, the rate at which you can read it is limited. So if you need to do a ton of data processing, at some point you need to split up your work into multiple machines. However, for a ton of applications, whether we're talking about like big online retail stores or other data analysis applications, for a lot of those, you actually can get the job done with just a single machine that has a lot of disks connected to it. And that's where relational databases are used. Okay, so this single machine design actually scales pretty well and allows you to run what's called relational database software. In this lecture, I'm going to be talking more about what relational databases are and what they support. Relational databases are basically like the original kind of database that became popular starting in this. Theoretically, was introduced in the 70s and like popularized through the 80s and was definitely already standard by the 90s and still in use today. It has like the most set of features that you'd find typically in any kind of database. But it's limited. They're generally limited to run on one machine. There's some companies nowadays that for certain applications will allow you to run with more than one machine to handle bigger data sets, but traditionally it's one machine. And then in later lectures, we'll talk about non-relational databases, which are generally called NoSQL databases, which were designed from day one to operate on lots of machines instead of just one machine. So they generally are capable of handling more load. We have a ton of lectures that talk about the differences between different kinds of databases, how some of them achieve more scalability than others. But again, today we're starting with the most traditional type of database, which is a relational database that runs on a single machine. Okay, and this is a little schematic drawing for what it might look like. Okay, so like I said, relational databases, you sometimes hear them called SQL databases because the language that's used to access the data is called SQL, the structured query language. And I'll show a little bit of what SQL language is in this class. Okay, now I started talking about databases. Well, I started talking about storage, different kinds of storage, databases. In general, persistent storage on disk has always been different than storage in memory. And databases, in some ways, are a way to make it easier to use persistent storage. So one of their benefits is, I guess that really the main benefit is providing an easy way to use persistent storage that solves a lot of the relational databases solve a lot of the like common problems that you would need to address when dealing with persistent storage. Because your programming languages that you use don't really have an explicit way to deal directly with storage. The exception to that is SQL, which is the relational database programming language. So when you're writing code in like Java or JavaScript or Python, the basic features of the language, the syntax of the language, is all designed to manipulate data that is in memory, not on disk. Data that will be thrown away when the computer is shut off, when the program stops running, even, right? So as a programmer in one of those traditional languages, you don't have an easy way to deal with persistent storage. If you want to deal with persistent storage, you have to use some kind of library to access files, right? You open a file, you read from a file, you write to a file, and whatnot. Okay. Now, the fact that programming languages don't support disks directly is not a terrible thing. I mean, one of the reasons for it is that originally computers didn't have storage, right? So in the early days, like storage, persistent storage, disk storage was like an optional feature. Okay, so it made sense that wasn't built into language. But even today, that persistent disk storage is a lot slower than memory. So it kind of makes sense that you'd want the programmer to stop and think before storing something on disk compared to using memory. But this means that it's really tedious to operate in large data sets because if your program is working on a large data set, it can't store it all in memory. You can't just use variables like arrays and hash maps and dictionaries to store your data. Like I know that you're used to, if you're kind of a beginning programmer, maybe in Python, like dictionaries solve almost every data problem that you have, right? But at some point, the dictionary gets so big that it uses up all the memory in your computer and the program crashes. Okay. At that point, you need to have some solution to use the disk because there's more capacity there, like shuffle data in and out. And doing that manually is kind of tedious and error prone. What databases do is give the programmer some kind of standard interface, which is called SQL, to work with persistent storage and to do it in a way that is performance optimized, in a way that like automatically migrates data between disk and memory as needed, and it gives you a language to access data in ways that are efficient, and it gives you ways to organize data in a way that it can be accessed efficiently. Okay. So let's talk a little bit about relational data modeling. So relational databases are just databases that store data in multiple tables. Like I said, this is a traditional kind of a database. The word relation actually is like a synonym for table. You might think that the word relational means, once you learn more about it, you might think it refers to the fact that different data elements have relationships to each other through foreign keys, which are these arrows I'm showing, but actually that's not what relational was defined to mean. Relation is a table. Right. But in common conversation about databases, the term table is more commonly used, and I think it also is more descriptive and more intuitive than relation. Anyway, so when you're using a relational database, you have a bunch of tables. The tables have predefined sets of columns. So it's like a very strict way of storing data, because if you're going to store data, it has to fit within certain tables that are predefined, that have certain columns. And what you do when you store more data is you're adding rows in those tables. So rows are added over time, and rows can refer to other rows through foreign keys, which are the arrows in these diagrams. And those are the two big concepts in relational databases are organizing data with tables. Tables have columns that are predefined, and then rows that are added over time to add more data. And then the second thing is foreign keys, which is the ability to link different tables through IDs. So an example of this I'm using here that I took from the book is like modeling LinkedIn, right? So this is showing the LinkedIn page for Bill Gates and all the data for Bill Gates that should be stored for his LinkedIn page. So to represent all this information about him, if we were to do it in a relational way, it could be done as shown on the right-hand side. So at the top, we have the main table, which is called the users table. Here I'm showing one column. It's actually wrapping around to make it fit easier on the screen. But this is like, the columns are user ID, first name, last name, summary, region ID, industry ID, and photo ID. Okay, so some of that information, like the name and the summary, is information that appears directly on the page that we're rendering. But other information is actually are references. Like the user ID 251, that's not really an inherent part of the data. That's more like metadata that is used internally to create links. And region ID also. So, for example, this user table doesn't say anything directly about, like it doesn't say Seattle, it doesn't say philanthropy. Instead, it has region ID US 91 as a foreign key that points to a regions table. In the regions table, we have a list of different regions, and one of those is Greater Seattle area, which has a key, an ID US:91. So when this region ID for Bill Gates says US 91, it's referring to this row here. That's why we have this arrow pointing. That's a foreign key. And with foreign keys, there's actually, when you create data and there are foreign keys defined on your schema, that matching has to be true. So if you tried to create a row where the region ID was some other number that was not present in this regions table, that would fail to create the entry because there was a foreign key error. Okay. By doing this, there's some benefits of doing this. I'll talk about that in the next slide. Notice also the industry ID refers to this industries table. Also, we have these other tables that give additional information. Like there are two rows here in the positions table that give information about Bill Gates. They do that by providing the same user ID, 251, that's listed in the user table. So this 251 here, all these 251s together point to this row. I mean, there should be, really there should be 6 different arrows, but just to make it clearer, all these arrows are joined together and they point to this one table. So the information about his education is in 2 rows because he has 2 different education entries. Those all refer to him with this user ID here, and so on. Okay. To get this final information about him, like all this information is needed to render the page, we would need to join rows from all of these tables. Joining is when you take a row and you use a foreign key to look up another row in another table, or even more than one row in another table, and get those rows and join it all together. Okay. So why do we have so many tables, not just one table? Well, it really comes down to the fact that you have to predefine the columns that are present for your rows, and every row in a table has to have data defined for all those columns. So in the case of regions, why do we have so many? You can actually stop and think about that if you want. Why do we have a separate table for regions? Well, the purpose of this is to normalize the data, meaning that if we have lots of users who are in the same region, like lots of users who are in the Seattle area, we can just write the word Greater Seattle Area once and refer to it by number from lots of places. So we save some space. There might also be, like in this case, we're not saving too much, but if there's additional information about the region, like the population of the region, the latitude and longitude of the region, that might be quite a lot of data about the region. And it would not make sense to repeat that for every single user in that region, right? By having just this external table with that information in this normalized way, that's called normalization, we have just this small entry for the user that points to lots of data that's shared about the region. Okay, so this region table will be much shorter than the users table, and will allow our users table to be reduced in size compared to a design that actually stored the data about regions within each user. So it leads to less repetition, basically. So normalization, that term in relational databases, means creating a schema, a design of tables and columns that minimizes the amount of repetition of data in your database, allows it all to be smaller, and that's a good thing because it allows you to fit more data, but also should make the performance better in many cases, although not in every case. What about positions? This table here for positions. Why do we have a separate table for positions as opposed to listing those positions in the users table? This one is actually a lot trickier than the regions table. So please stop and think about that. See if you can come up with a reason why positions is in a different table compared to users. Well, the reason for this is because we have to have the columns predefined in a table, and if we were to define columns for position information for users, we would have to know ahead of time exactly how many positions each user had, because we'd have to have a column for all the information. So in this case, Bill has 2 positions, like here they're listed here. So he has 2 rows in this table that correspond to him. Some other user might have 0 positions. So this schema allows it by having a user ID that never appears in the positions table. Or if Bill wants to add another position to his list, if he starts a new company or something, he can add a 3rd row to this table with also user ID 251, and the schema would support that. Now, a simpler design, or like a naive design, might add columns to the user table that says position, title, and position organization, but that would only support a fixed number of positions. Or you might say job 1, job 2, job 3 as columns in user table. That's a bad design because you have to hard code the columns, and that fixes the number of positions you support. If you have some users that have fewer than 3 jobs in that case, you'd have empty values in those columns, wasting space. And if you have a user who wants to have more than 3 positions, you would not be able to support it. So having an outside table for positions relative to users, that allows you to have, it creates a many-to-one relationship where you can have many positions for each user. Okay, so that's one of the key features of relational database design. When you're designing the schemas, that's something you have to understand. If you have a many-to-one relationship, then you need to create a separate table for those things that could be many. And that's also true for education and contact info. Same thing, right? Same reason there. Okay, so to summarize this, when we create a multi-table schema, if we store our data under multiple tables, that allows us to have many-to-one and many-to-many relationships. This one doesn't have any many-to-many relationships, but I guess depending on how you view this, you could view a user as a many-to-many relationship between regions and industries. Like every region has many users, and many industries has many users. And there are users that link each region to an industry, but that's kind of stretching things a bit. But that's why you have multiple tables, to have many-to-one, many-to-many relationships. To do that while having the columns finite and clearly defined, which is a a requirement of and a good feature of relational databases. So again, just to remind you, when we're talking about relations and relational databases, the word relation refers to a table, which is an unfortunate choice of words in my opinion, but that's just the way it is. So I often will, when designing databases, like if you're planning the architecture for a system, one of the things you might want to do is, you should do, is design the schema for your database. If you're using a relational database, that means like designing what the table should be, what their columns should be, and what foreign keys there should be that relate them to each other. So here's an example of what that process looks like. Actually, on the bottom part of this diagram is how I would draw a schema for this particular data set. So this data set is a staff listing. So you have people who are in certain rooms and departments, and the people are associated with different departments. Those departments are associated with different buildings. Now notice that you could join these together by like linking these out and repeating some of them to create one big table. That would be a denormalized design, but it would have repetitions. Like for example, both Frank and Sarah, not Frank and Sarah, both Betsy and Pat would have computer science and building 2 listed, would have computer science listed under their staff table, and they would also both have Ford and fax number 15503 listed under their name. That design's okay, but the downside of it is that it repeats information, so that's why we call it denormalized. Splitting it into tables like this creates a more efficient design. Now I'm showing this example with real data as an example, but if you're designing it, and once you get used to this, you should think about the tables just as with their table name and the columns that are defined within the table. So this is actually the schema. I'm just taking the headings of these tables, you see, and redrawing them down here. The underlined column is the one that is called a primary key, which means that it's unique, so you cannot repeat the ID for these things. And the arrows I'm showing between, in the schema now, I only have one arrow between each table to reflect a relationship that can be repeated that would be repeated for every row that exists. So every staff member, its department ID will link to a row in the department table, and particularly the ID row, just like we show here, all these arrows pointing from department column to this ID column. That is represented here with that arrow. Okay, and again, that's called a foreign key. And so this little drawing here is a nice, concise way to represent a relational database design, and should make sense to other people who know about databases, right? And designing this is a good prerequisite, is a necessary prerequisite before you start writing code and filling the database, because you need to define those tables and columns ahead of time. Until you do this and have a relation and really work out what the relationship is between them, you won't be able to get started, because you do have to predefine the schema. I mean, actually, once it gets going, there are ways to add. If you forget a column, you can always add it later using SQL commands, but you'd have to do that in a way that have to have some migration plan for the data that was already inserted, like a default value maybe to fill into a new column or something. Okay, so I used to teach a class called CS-310, Data Management and Information Processing, and there was one lecture in that class that covered relational database schema design in detail, lecture 7, and I have a link here to that lecture video, and it actually skips ahead about 4 minutes to the part where I start talking about the schema design. So I do recommend that you check out that video, especially if you've not taken a database course. Definitely, even if you have taken CS-310, again, I think that course doesn't really talk too much about schema design, because it doesn't talk too much about being a database user as opposed to being a database builder, like someone who's working at Oracle or some other database development company. So yeah, this is another lecture, and I'll also send out an announcement with this link to recommend that as well. But I still have more to talk about today. So once we store data in our database, we use the SQL Query language to access the data. And I'm not going to spend too much time like teaching you this in this class, but it is a useful skill, and it's fairly easy to pick up with some examples. So in this case, I'm using the schema with those 3 tables, like that staff data set that I was talking about before. And the SQL language is a declarative programming language that where you basically write out commands, which are like one thing that you want to do that involves pulling data from tables and presenting it, right? So in this case, it says select staff ID, staff name, and staff room, department name, department building ID. So it's printing out those columns that are being selected, which we see here in the results. Those are coming from 2 tables, staff and department. There's a word join between them because those tables are joined together. The way they are joined is by connecting on the staff.department ID equaling the department.id. So remember, there was a foreign key that related every staff member had a department ID, which is a number that connected to a row in the department table, that ID row. So this foreign key, this join condition at the end connects those foreign keys. And so by this command prints out the staff members along with the information that comes from their department name. So it links to the rows in 2 different tables, presents a sort of denormalized view of the data. And you also can modify, this is a pretty full-featured language, lets you compute things like averages and minimums and maximums. So it lets you do a lot of different kinds of data analyses on data that's stored in a database. And so you would either write this code yourself if you were like an analyst. So you might get access to a database through like a terminal type interface where you can just type out commands to get data. Like if you're working at a company and you're trying to figure out, I don't know, how successful was our last marketing campaign, and you have a database that has point of sale data, like cash register data, you might construct a query along, using this syntax to check to see how the sales of a certain product have changed over a certain day. So you'd be doing like filtering on certain product names and certain dates and stuff like that. That all are things you can do in this language, and you could type that out and get a result. So that's like a way of that's a mode of analysis where you're typing things manually. Or if you might also build these queries programmatically. So you might be a programmer that's developing an application. Like let's say you're building a social media application or an auction website or whatever that is using a database to store its data. So in that case, you might have requests that come in to render a page with, let's say, auction information. To do that, you need to get some data from the database. So your code would construct an appropriate select statement to read data from the database, filtering probably based on the auction ID or something like that. You get that data back in some kind of tabular form. There might be one row or several, and then your code would translate that into HTML that's appropriate, right? So like your code would generate appropriate SQL code to run on the server to get back the results, and you'd parse it and then translate and use it however you see fit, right? So this is a language that is both used directly by humans and also is generated by code. Okay. So why do we want to use a relational database? I touched on some of these, but let's review the important aspects here. So first, it gives us scalability in the sense that we can work with data that's larger than just the memory, so larger than the variables we can store in our programming language and the dictionaries and arrays and all that stuff, right? We can handle more data. We get persistence, which memeans that the data is stored on disk, whether it's solid state or magnetic. So when the program finishes, or you turn off your computer, you still have the data stored permanently somewhere. We have indexing. This I'll talk a little bit more about later. But not only are we storing data, but we actually have some built-in features in relational databases to allow us to efficiently sort and search in multiple dimensions. So I'm sure you all have learned about different data structures and algorithms for searching and sorting, and that all is well and good. It's good to know that stuff, but in practice, if you're storing your data in a database, the database kind of does that efficient searching for you, and we'll see how later. We also get concurrency, so we're storing data in one place where it actually can be accessed over a network by multiple users or applications at the same time. So again, remember that we have that traditional design where we have a load balancer in front, a lot of clones of a service, and then a database in the back. That database is being accessed concurrently by multiple clones of an application. Okay, and the database handles concurrency in the sense that it allows reads and writes to happen simultaneously, even though those might access the same location in the database. The database, has logic to make sure that doesn't cause any problems. We can do analysis now. So we get the SQL query language that lets us do all kinds of analyses, and there are people who specialize in their jobs, just like writing SQL queries to do analysis of data sets. And it's easier to do that in SQL than as opposed to writing in a traditional language because of all the built-in aggregation and filtering capabilities in SQL. It's really a language that is well optimized for the task of analyzing data that's stored in tabular formats. And there are also a couple other things of lesser importance to us right now. Integrity. So we define the schema with columns. We define the columns of the tables ahead of time so that when we insert data, we know that the types of those columns have to match what we've predefined. We have transactions to allow multiple things to happen at once, atomically or not at all, to get rolled back or not. We're not going to talk too much about that right now. We'll come back to it in a later lecture. The normalization of data eliminates duplication and waste, so we save space by storing common data in one place. And also we make that data consistent. So if we have more than one user that is in that LinkedIn example that's in, like, let's say the region Seattle, and if that table has information about the population of Seattle, like let's say the population is 800,000 people or something, if that population changes, we can change the population in one place in that one row for Seattle, as opposed to having to go through all the users and modify the population of their location individually, right? When the data is normalized, deduplicated, then there's just one place to make the change, so it's by definition consistent across all the places that refer to it. We also get some security benefits because we can databases are accessed over the network, and we can create different usernames with different levels of permission and privilege to access different parts of the data. You might have users that can just read data and not write data. Those are all features that come built into databases, which, all these things, many of these things you will need in your application, and databases are off-the-shelf applications that provide this, especially relational databases in particular, provide a lot of features. Okay. So, as an exercise, I want you to stop and think about which ones of these features you might get without using a database. In other words, databases are kind of complicated. They're available off the shelf, so as a user, you don't have to do too much to use them. But another alternative, which is in some sense simpler, is to just read and write files on disk. That gets some of these things, but not all of them. So stop and think about which of these goals we can achieve by just using files to store our data, as opposed to using a full-blown relational database. So the way I look at it, a file system achieves some of these things. In some sense, a file system is like a basic database, but a database gives you more than a file system. So file system does give you scalability in the sense that you can work with more data than can fit in the computer's RAM, right? You just create files to store that data. You get persistence, of course. You get some indexing, and you have to stop and think about how a file system gives you indexing. But especially if you know about the internals of how file systems are implemented, the path or file name of a file is a kind of index that lets you quickly find that data. Because data is if data is sitting on your disk somewhere here, the way the operating system quickly finds a particular piece of data is by you giving a file name for it, and it actually has a tree-based structure to navigate through the disk to find the particular location where that particular data is stored. I'm showing this in yellow instead of green because that indexing only works in one dimension. So you have one way to index your data by file name. If you want to access it efficiently through another way, that doesn't work. We'll talk more about indexing in a few more slides. There is concurrency in the sense that multiple apps can read or write data, but this can go wrong if you try to do things at once that shouldn't happen. In other words, if you want to support transactions, you don't get that like automatically from a disk or from files. Databases give you that. There's no analysis built into file access. There's no integrity or deduplication. We don't get those features from files. There is some security in the sense that we can define different. Most file systems these days allow you to have different users that have access to different files. So you might have a root user that can access everything, and then different home directories for different individual users. So you can do some isolation of data, especially like on a Unix-based system or really any system with a multiple user system. But again, with files, we don't get all of these; we just get some of them. Now, indexing is something relational databases do really well, and again, better than file systems. Just to introduce this topic in a few slides, when you're working with large amounts of data, it can be a challenge to find an item of interest. You want to be able to efficiently find it. This is kind of like one of the key topics in data structures and algorithms in general, right? So we learn about how sorting data is a way really helps tremendously in being able to find data, because you can do a binary search. So like a language dictionary lists words alphabetically, so that as a user you can do something like a binary search to find a particular word, right? If you look at a particular location, you compare that word with the word you're looking for, and then if it's greater or less than, you know whether you need to move in one direction or the other, and you can do that in a divide and conquer manner to find the particular location you want in log n time, in the worst case. But sorting doesn't always work. Sorting is not enough if you want to index in multiple dimensions, because what sorting relies on is the physical placement of elements in a certain order. But you can only do that in one way. Like, so if you have a products catalog and you want to find products quickly, either by the name, the manufacturer, or the price, sorting is not going to solve that problem. Like in your product catalog, you could sort by either name, or you can sort by manufacturer, or you can sort by price. If you choose to sort your items by price, then yes, it's easy to find what's the cheapest item, what is the 50th percentile priced item, which products cost $5. That's an easy question to answer if your catalog, your physical catalog of products is sorted by price. But if your physical catalog, but if you're sorting by price and you want to find all the products made by a certain company, like let's say Apple, that sorting by price doesn't help you to do that. You have to scan through every product and look for the word Apple in the manufacturer name, right? We also have a problem here that if we want to add new data to the data set and and the data is sorted, then we need to shift everything to make room in general, because we're going to have to insert somewhere in the middle of the data set for new data, unless we're always adding like higher priced items, let's say, if we're sorting by price, right? So it's a lot of work to accommodate just one addition, really not efficient, okay? Sorting also doesn't take advantage of the hardware storage hierarchy. So even if you do have just one dimension, that binary search you're doing across the whole data set will involve reads in dramatically different locations, which is not good for CPU caches. That's a little bit of a subtlety. But the first two are really are quite important and easy to see. So one solution to this problem that I found in a printed catalog. So this is the Granger catalog, which is a big catalog of industrial products that you can shop from. That you get that I have gotten in the mail. It has over 1,000 pages. It looks like 2,000 pages. It's kind of crazy actually, and there's a certain sorting of products. The pages are sorted by high-level product category, but then there are these additional indexes at the front of the book that give you references to find products in a different manner. So if you want to find product by product name, you can use these yellow pages, and these references are sorted by product name. So cups, curb, curbs, current, cushions, cutoffs, cutlery, cutoff wheels. So if you're looking for cutters, you can find that very quickly within these yellow pages. Now you won't actually find the cutters here. You won't find the full information, but here you'll find a reference. So there's a page number here for the different kinds of cutters. So if you're looking for an arbor cutter, you go to page 10. You go to these pages. It could actually be a list of pages where you would find the details of those products. Okay. Same thing is true for another dimension of the data, which is the manufacturer names. These blue pages here are an index of manufacturer names, and if you want to find all the products that are made by, let's say, a certain company, you would see them listed here, the page names and the page numbers, and you could go through and find those in the main catalog. So in this case, we are using simple sorting. So the main data is sorted one way, and then we have additional indexes that are added. So we created additional pages. So we required additional storage to allow us to quickly find elements in this main data set that would otherwise be difficult to find. Okay. And that same idea applies to relational databases when we have data that we want to store and be able to find it efficiently along multiple dimensions. But the way it's implemented is a little bit differently. So again, you typically wouldn't use sorting, because inserting elements, it's hard to insert elements in a sorted list without shifting everything. So generally you might have you either have a self-balancing binary tree or a hash table based index for data. So in these examples, I'm showing a self-balancing binary tree. So it could be like a red-black tree or a splay tree or something like that. Your data is stored, in this case, in like kind of a random order. Just whenever you get new data, you write it to the end of the list. So that allows you to add data efficiently, right? Because there's always space at the end. You just keep adding to the end new data as it comes in. Excuse me. But in order to find data efficiently according to different column values, you add indexes. So these are additional structures that you store, in this case a self-balancing binary tree, where the nodes, the values you're storing are the values of that column you're trying to efficiently access. So if you want to be able to find people by social security number, you can store all the social security numbers in a self-balancing binary tree, and that allows you to traverse down to a particular social security number in log n steps, right? Because this tree will only have at most log n levels. And once we get to the level where we find a social security number, we just have a reference that points to the particular storage location where all the details for that row are listed, right? So that's how you, and then when you add an entry to this table, you add a row to the bottom of the list of the storage, right? And you also update the self-balancing binary tree to have an additional node which points to the new entry. And of course, just like any with self-balancing binary tree, that addition should be efficient. It'll take log n time. It might involve some kind of a pivot or something to rebalance the tree, but overall, it's going to be efficient. And this is stored somewhere else in permanent storage and in memory. But this is much smaller than this because it doesn't store all the information about each row. Yeah, so a balanced binary search tree, as you know, is a sort of equivalent to binary search in the sense that it organizes data in a way that you can efficiently find any element by either navigating left or right down the tree, depending on whether the item you're looking for is greater than or less than the element you're looking for, you encounter. So if you're looking for 19, you start at the root always. You see 19 is less than 50, it means you go left. 19 is greater than 17, so you go right. It's less than 23, so you go left, and voila, you find it. Okay, and again, if this were an index of a table, this would point to the location in storage where all the details of this row are located. Okay. With a relational database, you don't actually have to worry about those implementation details of the indexes for the self-balancing binary trees and whatnot. That's one of the nice things about it. Like, you don't really need to know data structures to get the benefits of data structures because someone else has implemented it for you. All you have to do is run a command that creates an index on a certain column. So this is the syntax for creating an index for a certain column name on a certain table, this is just a SQL command you would run. There are different kinds of indexes. Usually you define a primary key on a table, which is a column whose value is unique for each row. Those are indexed by default, but then you also can add additional indexes to optimize other queries. Like it could be that for when you're looking at people, like you have some table of people, you need to query efficiently for people both based on the social security number. Maybe you also need to efficiently find people by name, right? There are two different things you want to be able to query on, so you need two different indexes for the two. So you have to create an index for two. So typical, either you anticipate ahead of time what your queries are going to be, and you add the relevant indexes to make those queries efficient, or you implement your system and you notice that certain operations are slow, like certain queries are slow, and then you look at those carefully and realize that, if I added an index in a certain place, that would make the query faster because it wouldn't have to do a full table scan. It could just quickly find the rows that are relevant for certain filtering. Usually it involves filtering, which is a where clause in the SQL language. So you can have multiple indexes in one table, and taking the same example of people, all it does is creates another one of these self-balancing binary trees that points to that uses the values from a different column in the table. So in this example, we have a person table that has 4 columns and 2 indexes. So it's indexed based on the social security number and also the birth year. So using either one of these columns, we can efficiently find entries. So in like log n time, these two queries, the first one is select star from person where social security number equals blah. So the where is like a filtering. This is going to be a fast query because there is an index available to find particular social security numbers. And again, as a programmer, you don't have to like implement the index or tell it to use the index. You just have to, as long as the index was created and you write a query that's like compatible with that index or can make use of that index, it should be used automatically and your query should be made efficient. The second one, the green one, is another query that can make use of indexing. It's a different index. It's that one on the right hand side. This is selecting all the people that have birth year between 1979 and 83. And this would give you that. I mean, the details of the tree are kind of skipped. Like these would actually be B trees, which support range queries. But the basic idea you should be able to get from this simplified view that I'm showing you. You also can have composite indexes that involve multiple columns. I guess this is maybe getting into more detail than you need to know at this point. But if you want to find, if you have a query, like for example, select star from person where first name equals Alice and last name equals Sanders. So we want to get the person that matches both of these things at the same time. To do that really efficiently, you can actually create a query that is, an index that combines those two particular things, and then you can find, this would point to the rows that have different combinations of the values. But that's not the same as having 2 indexes on the individual entries, because those would point to 2 potentially big subsets where these values are pointing to just the individual intersections of the 2 filters. Okay. That's more of an advanced topic. So this SQL language for doing queries is a declarative language where you tell the database what it is that you want to see. You do not tell the database how to execute the query. Like you don't tell it, go through this table first and use this index to filter down to a certain set, and then look at a subset of those where this other condition holds. What I just described, that stepwise process, is like an imperative style, which you're probably used to from Python and Java, JavaScript, whatever. Less so JavaScript, but Python for sure. SQL is not like that. It's more of like a functional declarative language. You tell it what you want to see, what the result should look like. You define the result, and it decides on its own how to calculate that result, and it tries to do it in the most efficient way. So it has a query execution planner that tries to make the best choices about how to generate the results. It's kind of like a compiler that runs on the fly on your query to figure out how to run it. If you end up getting a query that is slow, you can analyze the execution plan by using the explain command. That tells the database engine to like show you the output of that compilation step for it to tell you what steps it's going to go through to execute your query, and that might give you hints about how to improve the performance by, let's say, adding indexes. Okay, that's more like, these are all kind of more advanced topics. You need to decide. So when designing the schema, you can choose which columns to index. If a query is slow, then you can try to add an index to make it fast. Generally, if you're using where conditions, which are filters, then indexing on the column within the where condition will make it faster. If you're doing joins, where you have a foreign key referring to something else, then having an index will make those faster. Or if you're doing a lot of minimum or maximum aggregations, the index will make those fast as well, because you can use that tree to quickly find the minimum or maximum. Something like average, of course, would not be helped by an index because you still have to scan through everything to compute an average. Indexes are helpful, but they're not free, so you shouldn't just go through and add an index to every column just in case you need it. That's kind of a rookie mistake. If you look at these structures on the left and right hand side of the table, the indexes, those are consuming space. And actually, the amount of space they're consuming is not negligible. It's like on the order of the size of the table itself. It's like the size of one column in the table. So if you add an index to every single column, you're going to more than double the size of storage. That's going to slow things down. It's also going to slow down the performance when you add data, because when you add data now, instead of just adding it in the row, adding the row in storage, you also have to update a tree, which is the login operation, or multiple trees if there was the number of trees equal to the number of indexes you have, which can involve pivots and all that stuff. Right? So indexes consume space and slow down your inserts, but they can make your reads dramatically faster. Like if this is a big table, that could be very important. It's the difference between scanning through every single person in the table, like let's say millions of reads, as opposed to just log n, which could be just 10 reads. So the speed up can be really quite dramatic if you're using an index to find data, especially if you're just looking for one piece of data. If you're doing analytics where you're like computing averages over the whole data set and stuff like that, then indexes don't necessarily help because you have to scan through everything anyway. But for these like online transaction processing applications, like like e-commerce website or social media website or whatever kind of messaging system where you have users who are working with little pieces of the data, like their data, you want to be able to find their data efficiently, and indexes let you do that. Okay. There's a lot of different terminology, which is a little bit confusing for keys and indexes in SQL. I guess to summarize, if you encounter this, the basic idea, keep in mind that the word key and index are kind of interchangeable, or like a key is an index. There also are unique keys, which are indexes that don't allow duplicates. And primary keys are a particular type of unique keys. Like the first unique key you have in a table is a primary key, but you can have additional unique keys, which are then you could think of them as secondary and tertiary keys. And then finally, foreign keys are not keys themselves, but they're columns that point to keys in other tables that allow you to have references, like a certain ID refers to an element in another table. Because for these to work, the thing you're pointing to has to be unique in the other table, right? Because if you say, like in the case of Bill Gates, we said he was in, let's say in location 93, that location 93, for it to be meaningful, it should refer to one thing. It should be a unique key. That column should be a unique key in the other table that you're pointing to. Okay, so that was a long lecture. To summarize, we started talking about databases, relational databases. Persistent storage is something that requires special consideration in software, both because it's much slower than in-memory storage and smaller storage, and also there's a lack of language level support for persistent storage. So databases solve lots of problems related to storage, persistent storage, scalability, persistence, indexing, concurrency, and so on. You can kind of think of a database as like a file system, but like a lot better, like a more fully featured file system, because it has more indexing and better support for concurrency and security and stuff like that. and of course, importantly, it has this SQL query language that lets you do analytics, both programmatically and manually, depending on whether you're talking about writing code that interacts with a database or you're an analyst that's trying to answer questions using a database. Relational databases, also called SQL databases, store their data in tables, and the thing about them that is going to be like the learning curve associated with relational databases mostly is about figuring out how to define your database schema ahead of time. You have to define the tables and columns in those tables and the keys and like the foreign keys that link the tables. That takes a little bit of practice, but it's a skill that you should learn, because although we'll talk also about NoSQL databases, non-relational databases, still for the majority of use cases, I think that relational databases are the best choice because they're the most powerful and they are still pretty scalable, although not as scalable as NoSQL databases. Indexes are used to find rows quickly. So again, rows are elements that are stored in a table, and an index is associated with one or more column in a table. You can have more than one index in a table. And the SQL query language lets us run analysis code. One of the cool things about this that I didn't really mention, and one of the benefits, is that SQL lets you run analysis code near where the data is stored. So the database server could be in one location and your app is in another location. And the app sends a query to a database, let's say, to find the average value of all the products in our database. Now, the answer to that query is just one number. And the expression of that query is short. It's just like a small statement that says, select average price from products. So the amount of network transfer is very small. There's a lot of work involved in computing that query, because it might have to scan through millions of products and add up their prices and compute the average. It's much better to do that work on the database server close to where the storage is happening. That's pretty efficient compared to the alternative. If the alternative is actually fetching all of the prices, pulling them in over the network, loading them into your program, and then going through in like your, let's say, Python or Java programming language to compute the average, you could do that, but it would be a lot slower because you're doing all this transfer of data to compute that one average number. It's much better to do the computing close to the data storage. This is also a concept we'll come back to when we talk about MapReduce and Spark, which are for bigger scale systems. Those are the benefit of those computing models is also that you are doing the computing close to where the data is stored. Okay, so this is useful for filtering, aggregation, things like sums, counts, min, max, average, all that stuff. You want to do that as close to the data as possible. Okay, that's it. That was an intro to relational databases. Like I said, there's a link to another lecture that talks about data modeling, and you should check that out as well. All right, see you later.